capacity, that's that product, F sub u, times the tensile stress area. And then our specification statement will reflect that directly, which I'll show you in a minute. Just a reminder at this point that when you're calculating the force, you have to include the prying action. Recall, this was where I said if we have real problems in bolted connection design, bolted connection behavior, it most often falls into this category of bolts in tension, prying action, and sometimes fatigue added to that. I would avoid joints that, my preference is to avoid joints that put the bolts in tension if you can. Of course, you can't always do that, but especially if you have fatigue. Get the bolts in shear. The fatigue life of a bolt in shear is humongous. I have a slight preference for using A325 bolts in tension, as compared to A490s, just because they're a little more ductile. I would use A490s if I had to, but prefer A325 and minimize the prying action. So this direct tension problem, I put the bolt in, I put it in the testing machine, and there's what happens. I pull it, and that's almost the image that we did at more or less when we started. We don't quite do that, though, do we? We put it in by turning the nut on against the grip material. I don't like to use the term, but we torque the bolt. That's the term that we often use. So there is some tension in there at the same time. The fact of the matter is, though, that if we take the bolt that we've installed by torque, and that's the way we have to do it in an installation situation, and then we stop and say, well, what's the failure load of this bolt in tension going to be, if you'll watch? It just moves back to that original curve. It moves from one to the other, which is the same way of saying that the torsional stresses that are in there, they disappear. So how's that going on? Well, there's the installation. We apply that torque with a torque wrench or a spud wrench if we were strong enough. And how is it resisted? It's resisted by friction at the interface of these two plates. Got it? Okay, take those two plates apart like that. There's the resistance. And at ultimate, when I pull the plates apart, can there be any friction at that interface? No. There's no contact. There's no contact, there's no friction. In other words, this force that we started with here, as time goes on and we pull the parts away from one another, that torsional force disappears incrementally. And at ultimate, meaning the bolt fractures, there is no torsion left in that system. So we can design, as we were intending to do, on the basis of ultimate tensile strength multiplied by the net area, tensile stress area in this case. Another question, though, is if we have a pretension bolt in a connection, we still have a lot to talk about, and then we apply externally a tension force to the connection, maybe those add. So there's my tension, there's my connection, it puts the bolts in tension, and I'm applying external load, usually, as a result of forces in the system. Maybe the external forces that I apply and the internal, they're there because of the installation process, maybe they add. I'll give you the answer first and then we'll look at it. The answer is yes, they do add. The rejoinder is, but not very badly, or not very significantly. So that's where I'm heading. The equilibrium statement, sum of forces in the horizontal direction, according to the picture that I used to introduce this with, is that this is it, 45-degree line. There's the bolt force, there's the applied load, they're equal and opposite to one another. That's the 45-degree line. Got it? You're not used to seeing it in this form, but that's the way it is. Now, our starting, and it'll break when it hits ultimate, and that's where we want to end up. But we don't start from zero. We start from a point that's quite high on that vertical axis. That's the initial load. And again, because I can't show more than one image at a time, how we get from that initial load to that asterisk, which is the braking load, is on a sloping straight line that you see now on the image, and it goes on its way. That's the point of separation. That's when the parts separate, and equilibrium from there on is the 45-degree line. So our question is, in this working load range, the day-to-day life of this connection, how much additional load goes into the bolt as a result of external forces being applied in the tension settings. That's what we're exploring. Some free body diagrams. Simple connection, as simple as I can make it. No bolt pretension, draw the free body diagram. Sum of forces in the vertical direction, like that. Okay? That's what I've been saying for the last 3 minutes. The ultimate load is the product of the tensile stress area, or net area, times the ultimate tensile strength, like 120 KSI for A490 bolts, A325 bolts. Now, a second case is just the pretension. Then we'll combine them with external load. So if there's just pretension, that's the T sub B in the bolt. There's some compression between the connected parts. It has to be in equilibrium. That's the only place it can show up. I don't know what it is. C sub I it is initial. And they're equal and opposite to one another. So I have a second piece of information. Now, the two act together. I've got the external force, and I've got the internal bolt force, which is the pretension. And I know that, I can presume that they're going to be different. In fact, the bolt force goes up, and the compression force goes down. We don't have to know that, but we may as well use that to get along. So in this third view, the equilibrium statement says that the final bolt force, T sub F, is equal to the final compressive force, which I'm not particularly interested in, plus the applied external load. That's the information that we have at this point. You'll notice that we have two unknowns, the bolt force stuff and the compression force stuff. But how many equations of equilibrium do I have? Well, in principle, 3, but here I only have 1 available to me, sum of forces in the vertical direction. The other 2 are self-satisfied. So I've got more unknowns than I have equations of equilibrium. So back to your second year. Boy, it's got a long way back. And what did you do at this point? It's a statically indeterminate system. You needed some information, and what you use, more information, and what you use is about deformations. Deformations, what's he talking about? It's an axially loaded member. What's the deformation of an axially loaded member? Well, you all remember that, PL over AE. Okay, so write that. For the bolt, the deformation of the bolt, the P, I'm going to write it as change in bolt forces. It'll get us to our answer faster. What's L? L is whatever you want. I took a plate thickness. Because it drops out, it doesn't matter what you choose. PL, A, area of the bolt, obviously, E steel. Write a similar expression for what's happening in deformation terms in the plate. Plate deformation, delta T, is, again, a change in compression forces in the plate. L, use the same L as you did on the left-hand side. A, area of the plate, and E. They're equal to one another. So it's a deformation closed system. They're the same deformation. So set them equal to one another. Of course, the E's cancel, the T's cancel, and we're left with this relationship, and use that to obtain, and the previous equations, to obtain the final bolt force, which is what I want, equal to the initial bolt force plus a fraction of the external applied force. Let's put that on the next page. So that's what we want on the next image. So I want that. Well, I know what the area of the bolt is, but what's the area of the plate? It's the area of the plate associated with a bolt. I don't know uniquely what that is, but with some more background, some analysis, but particularly tests, a reasonable value for that is about 9. So if you use 9, you get an increase of about 10% over what you thought it was. In fact, physical tests show that it's more like 7 or 8%. And 7 or 8%, for specification writers, the choice now is to say, well, let's make them calculate that, or let's bury it in the design expression. And that's the sensible choice in this case, where 7 or 8% can be accommodated. So to repeat, the answer to the question, does the application of external tensile forces to this part increase the bolt tension force internally in the day-to-day life of the bolt? The answer is yes, it does, but not very much. So there it is. So that's the result of the examination that we've made at this point. So the rule, finally, says phi, the knockdown factor, resistance factor, R sub n. Early on I said we're just going to calculate R sub n. I'm always choosing L or FD format because it suits me, but it was R sub n, same R sub n in allowable stress design. Trust me, it's the same thing. Okay, it's phi F sub nt, a quantity, area bolt. Okay, that's the design tensile strength, phi R sub n. That's the nominal tensile strength. What do they mean by that? I'll have to explain. An area bolt. But he just told me that I'm going to use a so-called tensile stress area. But this bolt area is pi d squared over 4. In other words, it doesn't include the threads, the effect of the threads. So there's something going on here that I have to take account of. Well, in fundamental terms, I said it's F sub u, 120 for A325 bolts, times the tensile stress area. Work it out, look it up in tables, whatever. On average, for structural size bolts, the tensile stress area is about 0.75 times the pi d squared over 4. And that's what we use. It doesn't vary much from that quantity. So we'll go back. We'll adjust the area that way. We'll go back and write this in our equation, the 0.75 S sub u AB. Okay, comfortable with that? At this point, we'd call this F sub nt. That's the design tensile strength. So that rule that I showed a couple of images ago that AISC writes for bolts in tension says F sub nt is 0.75 F sub u. Now I know it's a lot of stuff to keep coming at you, and I keep throwing questions at you. Are we really saying we can only use 75% of F sub u? No. We're saying we can use 100% of F sub u, but we've got to adjust the area. Naturally, the 0.75 gets thrown out in front. That's the way we tend to be. So the 0.75 has nothing to do with F sub u. It's an adjustment to the area. Now, I don't know how that's going to change your life, but there it is. All right, we're working our way through free body diagrams that I did quite a long way back, and we still have the bearing capacity of the connected material to deal with. I'm showing it for tension member case, but it doesn't matter whether it's compression member case or not. It'll cover it. So the action is back in there. And there are two issues. Either, as you logically would conclude, either the shear out of a block of material in this region where the plate is pulling up against the bolt, or yielding. If that doesn't happen, if the bolt is if the end bolt is far enough back into the connection, maybe that doesn't happen. Maybe it doesn't shear out, but you'll get excessive yielding. And so we need that rule as well. So with some dimensions here, which I won't pause on, we need these two rules, and we'll write them. They're reasonably coherent. They work pretty well. The shear out it's shear. Look at the shear surface. It's L sub c long and T thick. There are two of them, one down each side. So write it that way. It's shear ultimate. However, what's shear ultimate? Shear and tension. In this case, we use 0.75 times sigma ultimate. And we hadn't used that before. We used 0.62. The solution here is a little too conservative. So an adjustment in the conservative, to capture the conservatism, is made on the 0.75. You just have to go with that. It's reasonable. The shearing out length is really longer than the one in the model shows. So we use that, and so the result is the rule that you see in your specification, 1.5 times F sub u of the material times a length times a plate thickness. So we need we got one rule, we're almost there. We need the deformation rule. The deformation rule comes largely from tests, and it says that, it reflects that the bearing stresses, sigma b, as a ratio to the plate ultimate strength, is about the same as that end distance, L sub E, to the hole diameter, D. We want the bearing stress, so solve for it. That's in the next line. The bearing stress then is whatever. And what we really want is the bearing capacity in terms of a force. So multiply that by an area, which is the diameter times the thickness. Do the algebra. It's just working step by step. And we find that that's valid for lengths greater than 3D. If it's not greater than 3D, then it's going to shear out. We've covered that. Here it's more than 3D, so it's yielding. I'll just change the notation from sigmas to F sub U to be consistent with the specification. Throw that all back in there, and there's the rule for deformation limited case 3dt F sub U. And finally at this stage, without phi values, I just didn't insert them, it's 1.5 F sub U L sub C times T, or less than or equal to 3 dt F sub U. So the first one is shearing, and the second one is excessive yielding. Might be a better way of putting it. Got it? That's it's not El Perfecto. It could be more sophisticated. At this point, as a designer, you don't need more sophistication in the design rules. You want design rules that are reasonable, they're understandable. I know it's tough out there. Specification writers think they're writing them as coherent, but it doesn't always work out that way, does it? And then you put the phi value in. One further note is that at this point the specification says, but when deformation is a consideration, you take 80% of that. We're seeing a lot of 80% in this discourse. This is a different one. It just says, if you think deformation is going to be a problem for you, too much deformation, then take 1.2 and 2.4 instead of 1.5 and 3. I'm not, how do I put this nicely? It's going to show up later. I'm not a supporter of that. It's based on getting a limit of deformation of 0.25. Well, that's not a lot of deformation. We're talking about ultimate. Does a quarter of an inch of deformation at ultimate concern me? Doesn't concern me. I can easily go to 3/8 or even a half, depends on the other dimensions. And we're talking about things at ultimate. So I didn't like the test conditions either. And looking at tall buildings, even using oversized holes, I don't find the bearing capacity statements 1.5 and 3 to give any problems. I wouldn't take that discount. Okay, so that's a bunch of stuff on fundamentals followed by specification requirements. I know you're thirsting for real stuff again. Here's a gusset plate. It's tested. Of course, this is leading somewhere. And what do I see? Well, the 45-degree lines are there for the purposes of they look like chalk lines. They're there for purposes of the researchers. Don't have to worry too much about them. Happened to be a gusset plate where the free edges were stiffened. You can see that at the top right and the top left. And what information can we get from this? What does he want to tell me? Do you see stuff, don't you? You see holes elongated. Look at the top two holes. The next pair down, the next pair, the next pair, the next pair. If I tell you, I'm going to tell you, this is the load at failure. What can you tell me now? You have to write a design rule. Do you see failure? Do you see the failure? How often do I have to ask you that? You don't see the failure? There's the failure right there. I know. I see the failure. I've been there. That's the failure. It's fractured there. It's fractured in tension. I talked about deformations a lot this afternoon. I said shear deformations are big. Tension deformations are okay, but they're not nearly as big as shear deformations. Trust me, this is the load at ultimate. You're not going to get a higher load than this. You can pull it apart, but you don't get a higher load than this. So now we would ask, write the design rule. Can you write the design rule? Of course you can. A little nudging. Tension fracture, and some of you can see it, but not everybody can. Shear yielding up and down these two sides. Do you see fracture through the holes in the shear sense? No, doesn't happen. So there's a block of material there. That's the issue, and we call it block shear, don't we? It's kind of a poor label now because it implies that there's going to be shear fracture, but there isn't. That's what we're used to seeing if you're a student of this. But this is after the test. This is after you've gotten the maximum load, which was my previous image. You stop the test, you stand around, you congratulate yourself that nobody was killed, you kick the testing machine for a while, and then you say, what do we do next? And everybody says, oh, well, pull it apart. It's a lot easier to get out of the testing machine, too. So you pull it apart, and this is what you see. But this is not the condition at ultimate. Trust me, it just isn't. There are lots of block shear tests now, and this is not the way it happens. So there's been a change in your specification regarding the block shear rules, and they reflect what I'm trying to give to you now. And a reminder or reinforcement that the condition, ultimate load condition, is attained when the shear fracture across that little ligament, and it's not reflective of the geometry. With reasonable geometries, this is always what happens. So you write the rule. I'm just going to write it the way I would write it as a researcher now, and you say, oh, tension fracture, yeah, in that area, through those two holes, F sub U, tension ultimate. Going to have to throw a phi factor in it. Shear yield up the two sides. It's gross shear area now. That's important to, let me pause on that. It's not on net area. It doesn't shear through the holes. It shears along the edge. And it's shear yielding, so that's the shear area, and it's F sub Y. And 0.6 times F sub Y will give us a reasonable representation of the shear yielding stress. There are some other requirements, particularly for cope beams. I'm not going to take this farther. However, I will show you a cope beam test just so you benefit from seeing failed specimens. And these are with the cope beams, they're very hard to stop the test, so they weren't able to. And you say, well, it went through the hole. It didn't go through the holes. It went right along the edge and then subsequently opened into the holes. So with some adjustments for the fact that there's an eccentricity present in this connection that wasn't in the previous one, the same kind of model will serve very well. So you have a rule for that. We've kind of installed the bolts, but we've got to go back to that. So here's somebody installing fasteners, and we have a lot to say about that. Now, in a so-called bearing-type connection where we don't need the pretension, because it's not slip-critical or other conditions, they can be installed to snug-tight only, which is the ordinary effort of a worker using a spud wrench, or it's the first impact of an impact wrench. That's a pretty vague description, so I'll have to try to justify that. There's going to be some bolt force in there, but we don't know how much it is. It's small, it's a little, or it's more than a little, but we're not going to count on it being anything. So that's what we're doing. Here's what we're doing. We're turning the nut on, elongating the bolt after the parts are in close contact. I've said that several times, and away we are. Now, the next method of installation will be what's called a calibrated wrench. And the first thing to get out of the way is, any mechanical engineers in here? Any mechanical engineering handbook that I'm aware of will have a formula that relates bolt pretension to torque, to applied torque. We feel so strongly about it that the specification says you can't do that. You're not allowed to use a calculated value. It's just too variable. It's going to be 40%, it's going to be 40% out. So to think that you're going to do it by calculation, the answer is no. You can't, and you're not allowed to. I guess those two go together. But if you want to install this way, you can calibrate the wrenches that you're going to use so that you do get the pretension, the 70%, whatever. So that's possible, no quarrel with that. How do we calibrate it? Well, here's a air impact hammer using a device. This is a trade name, Skidmore Wilhelm manufacture these. It's nothing more than a hydraulic load cell. You put the bolt in, you're compressing plates. There's fluid between the plates. This is calibrated to a gauge, and you read the pressure. It's easy, it works well. Great. So you set the wrench to stall or cut out at the predetermined value, which is 1.05 times the minimum value. You're asked to introduce a 5%, there's a 5% hardship value because you can never calibrate as much bolts as you'd like statistically. You have to use 3 bolts minimum. It's unique to whatever that lot of bolts is. And that length, that diameter, that grade of bolt, the conditions. So if you're installing 3-inch long A325 bolts of 3/4 inch diameter this morning, and you're installing 4-inch long A325 bolts 3/4 inch diameter this afternoon, you have to do new calibration. That's it, folks. There's just no choice. The characteristics are different. Anytime conditions change, you have to recalibrate, and you have to calibrate a minimum of once a day. So people who want to use this have to be, well, if you are on top of things like this, that's fine. You have to use washers to establish a baseline friction condition.